Before we talk about why that's the case, let's go back to think about what we have learned in the past. There are three kinds of heat transfer method. One is called conduction, the second one is called convection, and the last one is called radiation. However, in IGCSE, you only learn about the qualitative idea of these three only. You never learn about the quantitative formula to describe the different factors or how different factors will affect its rate. You may recall that there is an equation called Q equal to mc delta T you learned in chapter 3 or even in IGCSE as well. But remember, that one doesn't specify which kind of heat transfer method that you're referring to. It's just talking about when the energy got transferred and reached thermal equilibrium. That's the way you can estimate the energy. But in terms of the speed or the rate, you don't know at all. Okay, so let's talk about conduction first. In fact, the formula for conduction is not in the IB syllabus. So if you like to, you can ignore it. But then I guess I would like to spend maybe a minute or two to appreciate the idea of the formula. So you can see here is the formula, which is delta Q over delta T. That is the rate of heat transfer, equal to K times A times delta T over L. So imagine the picture on the right hand side. K would simply be depending on the conductivity, so it's more about the material itself. So for example, for copper, for aluminium, for iron, they all have different rates of heat transfer, even for insulator as well. And as for A, which is the cross-sectional area, and obviously that depends on how much contact area that you're having. And you can imagine in terms of the molecular structure or atomic view, the wider, the more area that you have between the two objects, more area they contact, then of course it will be higher the rate. Same for the idea as in the temperature difference, delta T. Imagine you are having two objects that are of very different temperature, then the rates that they change the temperature will be much faster versus maybe the other top object that is of only 1 or 2 degrees Celsius of difference. As for the length, obviously the longer the length is, the harder for the heat to transfer through conduction, because you know for conduction it has to be by vibration colliding on to the other particle one by one. So that's why for things like the hot pot or any kind of kitchen tool, usually there is a long handle so that the warm part of whatever that you are doing with the fire, the cooking, would not be transferred that quickly to the part where you are handling. Okay, so once again, this equation of conduction will not be in the IB exam, so don't worry if you cannot really understand right now. The second thing that we would like to talk about is the convection. And for convection, if you try to go through the textbook, you don't even find there's a formula. And if you're really interested, let me show you very quickly. NANI? Okay, so here is the formula for the convection. And as you can see, the temperature difference, once again, play a very important role here because when you are of the same temperature, then there's no any kind of thermal transfer at all. The other thing that you may consider would also be the area and also some sort of coefficient. Again, it mostly are just depending on the material, the medium that you are dealing with. So that's the equation, and probably because of the syllabus is having limited time, therefore we cannot cover it. So yes, it's not in the syllabus as well. So the actual thing that we would like to talk about here is radiation, right? And that's why in this video I spent around 10 minutes to talk about radiation earlier. I mean glowing earlier, and that is because those will be referred as radiation. Let's take a look at the equation first. So the name of the equation is called Stefan Boltzmann law, which you can see the equation here is P equals to E sigma A T to the power 4. So if you are interested to know how to prove it, you can read through Wikipedia simply, and I'll put the link in the description. You can start from here, NANI? And eventually you find out the equations here. Alright, so for the first letter in the equation, it is P, that is obviously powered. It also means energy per second radiated by body here. Remember, it is radiation we are talking about, so nothing to do with conduction or convection. For the next symbol, you can see is emissivity, and this is a variable that depends on the material itself. It can only be within 0 to 1, and you may wonder, so what exactly it is? If you recall in IGCSE, there's something called the Leslie cube, which is the one that I'm showing. It's simply a box with different color on each side. Some of them are silver white, some of them are so-called the matte black or dull black. And so you find out because of their color, the silver white one may not emit as much radiation, so that's why the temperature is somewhat lower if you pour the hot water inside the cube, while the matte black, that one, would emit much more radiation because it's a good radiator. And so the temperature you measure from there will be much higher than the silver white. So put it back in the context of emissivity, that means the one with black color will have a higher emissivity, the one with the color of shiny silver will have a lower emissivity in this case. If we put this into extreme, when E equals to perfectly 1, then we'll call that body as something called the black body. However, this is just a theoretical idea. It doesn't really exist in the world. A similar idea, and that is called in physics rigid body, and that is talking about the object cannot be bent at all. In fact, everything in our world has a little bit, right, if not very elastic, but still whatever you use, there is still a bit of elasticity inside, so you can kind of extend it or compress it for a certain extent. So there's no really perfect rigid body here. So same for black body, there's no perfect black body. However, for the emissivity for the stars, including our sun, is a very good approximation to black body, so it's very close to 1. At the same time, this is called VANTABLACK. So if you watch the video right now, you see actually there's something inside you didn't notice, right? It looks like a black paper. And this is the best we can do so far. And it is called the so-called darkest material we can find on Earth. It's not really fine, it's artificially made. What happened is, inside there are very tiny in nanoscale tubes, which when the light go in, it cannot reflect at all almost. It is said that it can only reflect for like 0.04 because 99.96% of light are being absorbed already. So this is a really cool video and also material. You should check it out. I'll put a link in the description below. Let's play a game here. You can see there are different kind of surfaces on the lids here, including black body, which obviously the emissivity is 1. But then for ocean water, ice, dry land, and land with vegetation, I want you to rank them. So in whatever ascending or descending order. So pause the video right now, try it out, and we'll look at the answers later on.
A few moments later.
I'm not sure if this happened to you, because when I first learned this, I was quite surprised by the fact that ice has a really low emissivity. Do you know why? The reason is because the snow or the ice will be very reflective because of its color. And so that's why you can see people will wear those sunglasses when they go for snowboarding or skiing. And yes, this is me, by the way, and this is Mr. Chen. And you should also see that for the ocean water, it has the highest emissivity here. The reason is very simple, because it's basically transparent, so most of the light can actually transmit through it, while for the other 2 or 3 you can't, and so the emissivity is slightly lower. The next letter in the formula would then be something called the Stefan Boltzmann constant, which is just a constant we find from the experiment. So I guess you don't have to care about it much right now. The next symbol is A, and be careful with it. Here, the A is referring to the surface area. Okay, so when we talk about a body, usually we will refer the body as a sphere. So usually, especially for planets, so usually we'll be using the surface area equation for the sphere to calculate. If you think a bit deeper, mathematically, when A increase, P will also increase. So in a more physical context, what you can think of is maybe you can think of there are two maybe black color of bottles, but one is much bigger and one is much smaller. So if you pour the same temperature of water, say boiling water in it, the one with greater surface area, that means the bigger one, would surely cool down first. I mean, that's pretty much very intuitive sense. And lastly is the parameter of temperature. Remember, we have to use the absolute temperature. That means in the temperature of Kelvin scale. And it should be also very intuitive to you as well. If you think about the body with a greater temperature, that means it must have a greater kinetic energy. And so when they try to emit the energy, they surely can emit more per second. However, as the old saying, no man is an island, that means nothing can really be insulated from the world. So if you think about when an object is emitting radiation, it's also receiving radiation from the surrounding. So that's why you can see there's an equation here for the actual power, for the net power. You actually have to apply this equation twice. One is for input, one is for output simply. So of course you have to substitute the temperature accordingly. And so when the temperature is the same, then obviously there's no net power. Just like if you recall just now when I showed you the equation of conduction and convection, the first very basic requirement is to have temperature difference. So that's why you learn in all the way in the past 2-3 years, whenever there is a thermal energy transfer, there must be temperature difference. Same for radiation as well. So now you basically understand the idea of the Stefan Boltzmann law equation, but then you probably still cannot explain what I asked you in the previous video. Again, why would the Bunsen burner of different color when they are of different temperature? Same for the sun, same for us, why do we emit infrared rather than visible light? You will need to use and understand one more equation. Here is the Wien's displacement law. And what it said, it is saying that for the maximum wavelength, which is amongst the electromagnetic wave that you emit, times the T, which is the temperature of that body, will equal to a constant. So yeah, it's just a constant, 2.9 times 10 to the power of -3. This is something you have to use. So let me give you some time. I will explain in the next video. So right now, I want you to think about the question that I asked you in the previous video. I'll see you again in the next video. Bye.